Third presentation of the day is from group number 4, and they have looked in harvesting energy. They have brought some props here, so they're probably going to explain what it all is and how realistic this is. And there are 2 presenters for this theme. Mart is standing here, he will kick off, and then Pranav standing over there. He will do the second part of the presentation. I will dim the lights for them, and then the floor goes.
Yes, thank you, Mr. Melkert. We're going to start off with a little quiz question for you. So we're going to talk about TU Delft's energy demands, and we're going to compare it to an average Dutch household. Now we're going to call some numbers, and if you think that is the energy requirement of TU Delft compared to a Dutch household, you raise your hand. So first of all, who thinks TU Delft consumes the same amount of energy as 100 Dutch average household? And it's safe not to go for the first option indeed. Who thinks it's 900? It's a bit more already. I see one hand over there. Who thinks it's 3,500? You can see some more hands, quite some more. Okay, let's go a bit higher. Who thinks it's 9,500? It's quite a big village. I see quite a lot of hands now. 15,000? Anybody? Some more hands. Final option, 20,000? A few hands still. Well, it's not more than 20,000 because that couldn't fit on my slide. But basically, the answer is 20,000. So for 25,000 students, our university requires almost a household per student. And we were tasked to supply TU Delft with that energy. And when I say we, I mean this team over here. All happy faces, this was the beginning of our project. And we've called our project the GreenHyve. And the mission of GreenHyve is stated here above. And simply said, what it means is that we'll design a system which will fly above the low layer cloud, so above 2 kilometers we defined that, and harvest energy for TU Delft. And with that came some sub-requirements like being weatherproof, being cost-effective, being scalable, being area-effective, and if possible, we should make it of renewable or sustainable materials only. Now you might think, how do you harvest energy above the clouds, because there's not so much there. There are several things you can do. You can harvest solar energy, you can harvest wind energy, you can use thermal differences for energy generation, you can dissipate energy from the clouds, and you can use gravity to harvest energy. But you must be thinking, why would you even go above these clouds? Now for us, the first reason was because our customer wanted us to. But of course our customers has thought well of this, because there are actual good advantages of going there. The first one is that you have more wind. The average wind speed at, for instance, 2 kilometers altitude is 10 meters per second, whereas here on Earth in the Netherlands, it's only 3 meters per second. Now these winds are also more reliable, both in terms of well, magnitude, but also in orientation. And if you hide your system above the clouds, people won't be bothered by it so much. Finally, there's more sun. As simply said, the clouds won't be blocking the sun. Now, we made a design starting from this, and we'll talk you through our design in these stages. We'll talk about how we came to a concept, we'll talk about the technical details, we'll review our design, and we'll take a look in the future. And in the right top, you can see an icon which indicates at which phase we are. In the left top, you can see a battery showing the progress of our presentation. We started our design with a brainstorm, and we went as wide as possible to cover all the opportunities there are to harvest energy. So we even looked at satellites with solar energy, because that's also above the clouds. We looked at cloud dissipators who suck up the clouds and generate energy from that. We looked at space elevators. We looked at drones flying through coils. But in the end, from those hundreds of ideas that we had, we needed to come down to a few less, which we could deeply investigate. So we decided in a few steps to get to 3 system concepts. And it was shown over here. The first one is a swarm of balloons carrying solar panels who wirelessly transfer the energy back to Earth. The second option is a tethered flying kite or a glider which pulls on a tether and generates electricity in that way. And the last option is taking a wind turbine, putting it on a wing or a balloon, flying it up in the air and let it do its wind turbine thingy up there. Now we investigated all 3 of those options and we made a trade-off of it. And I'll show you the quick highlights in here. So one big advantage of the solar balloons is that it's not connected to the ground, which for the design is, makes it a lot less complicated. Furthermore, it generates its electricity for subsystems on board already, but it also has some downsides. The wireless energy transfer takes enormous antennas with a lot of material, roughly the size of a football field. Furthermore, docking is quite difficult. If you need to maintain it, you need to get it down, but it's hardly controllable as it's just free floating with the wind. And the second option had some advantages as well. It has a tether, although it's quite lightweight. It only needs to carry tensional forces. It can harvest quite a lot of energy and it's controllable and relatively small. The downside of this is if you go to 2 kilometers and you tether it to the ground and you start sweeping it around, it will create a lot of drag. So that's quite a downside of this concept. Finally, it has no onboard energy generation, so we needed to find a solution for that as well. And our last option has that perk. It has the onboard energy supply. However, there were some downsides to this system as well. First of all, it needs an electrically conductive cable, so probably copper or aluminium, and you might imagine that if you run it up to 2 kilometers high, that's going to be extremely heavy. So you will need a huge wing or balloon to carry it up, requiring a lot of material. Now, as you might already see a bit from this slide, design 2, in the end of the trade-off, was our winner, so we decided to develop that further. And it uses crosswind flying, which is a counterintuitive concept for some aerospace engineers, so we'll explain it using the analogy of a sailboat. If you have a sailboat and wind is coming from the direction of the arrow, what you would first expect is for the sailboat to be blown away in the direction of the wind. But that's not what happens, because the water is stopping it. It has more resistance in sideways direction. And therefore, with side wind, the sailboat can go forward. We can do the same with aircraft, except for we don't put it in the water, but we put a tether on it to keep it fixed in that direction. And if you have wind coming from that direction, it will do somewhat the same and it will start flying forward. And if you fly it in circles, it will have enough energy to create lift, which keeps it airborne. Now you can imagine the pulling forces on this tether are going to be quite big, and you can use those pulling forces to generate electricity using a ground-based drum and generator. So you pull out the tether, the drum will start to rotate, and that will drive the generator which harvests energy. Now I already addressed one of the problems with this, and that is the drag of the tether. And as you can see a bit from this image, if you sweep around the entire cable, it's going to cause a lot of drag, which reduces your performance. So instead we chose to go for a Y-tether, which is seen over here. You can see it in the model. If the wind starts coming in and it starts flying in circles and circles and circles, oh, it doesn't sound that easy to circle, then this part of the cable will actually stay stationary. It won't move. And therefore, it won't have that much drag, which enhances our performance quite a lot. After the design, we recalculated it and we find that the right design had 5 times less drag than the left design. Now that we've set up our concept, we can start designing it in detail, and we used quite a special philosophy for that. We started off using renewable or sustainable materials only, as was our requirement. We analyzed the performance, and only if they would not meet requirements or couldn't perform, we would switch to tougher, non-renewable materials who could meet the target. Furthermore, we focused on the entire system, so not only the technical aspect, but also things like cost and safety, keep a broad perspective, and we focused mainly on the innovative parts of the design that really set us apart. We designed it using an iteration loop, so we made several scripts, or we used several programs, for instance XFLR5 for the aerodynamics. We combined those inputs and outputs and then optimized it. You just basically run it through the iteration a few times until it converges, and that was our optimal system. We verified it using a few different checks. We used sanity checks, unit checks. We performed hand calculations of all the loops. And we used as much as possible textbook methods because they are verified as well. Well, this led to the sizing of our system. First of all, we have a glider over here. It's 2 gliders of 60 square meters in wing area. They will each weigh about 3,000 kilograms. We first tried designing, for instance, a wing box with bamboo composites, which are actually a thing. But it turned out that the wing box would be bigger than the wing, which of course is inconvenient. So in the end, we decided to use a composite of PEEK and carbon fiber, but within that wing box, we have a supporting structure of balsa wood for some quite thick ribs in that wing. And we also designed the tether. It's going to be 1.5 centimeters thick. It's going to be quite heavy as well, 2,300 kilograms. The moving part, so up here, the rotational part will be about 1 kilometer, and the stationary part will be about 4 kilometers. We started out using banana fibers as a material, and some of you might laugh at that, but banana fibers is actually one of the strongest natural fibers there is. But in the end, the tether would become too heavy to fly, so we had to switch to a non-renewable material again, which was Dyneema. Now that we have a design, we can start operating it, and Pranav knows a lot about that, so he's going to tell you more on that.
Can you hear me? Right, excellent. So now we've detailed all the steps that we took to actually develop our system. But how does our system actually work? There are three main parts. There's the takeoff and landing procedure, there's the reel out phase, and there's the reel in phase. Let's start with the takeoff and landing procedure. As you may see from the image above, we have a circular runway. One advantage is that we have pretty much an infinite runway. We can just keep spinning round and round until we have enough speed to take off. Another advantage is that we don't actually pull the entire length of the tether, just the tether above the Y connection, which is extremely handy for us. Now, the downside to this is that for each system, we will have one runway. Now, if you take a look at the video provided by Dr. Cherubini, we show you how the takeoff procedure works. After we generate enough speed, the gliders start taking off. Although they spin in circles, they do vertically take off until they reach an appropriate height and tether length. Once they reach this tether length, it's time to actually orient it down to a certain elevation angle. This elevation angle, as you can see, is the point where we can optimally start harvesting energy. And it's at this phase where the next phase starts, which is the reel out process. As you may see, they fly in circles, and the radius of this circle is approximately 466 meters. Now the reel out phase. This is where we actually pull the tether out of the drum. We pull out approximately 800 meters worth of this tether, and it happens for around 4 minutes. So we originally start at an altitude of approximately 2.7 kilometers, and it keeps pulling until 3.2 kilometers. We generate approximately 635 kilowatts of power. But now, after we actually pull it out the full 800 meters, we need to reel it in again. And this is called the reel in phase. We have a winch connected to the drum that actually reels it in. This takes around half a minute, and it requires about 6 kilowatts of power. Now maintenance, as you may imagine, is very, very important. We have backup gliders to make sure that we keep all our systems airborne and generate the most amount of power. However, we must change the tether very often. The tether, the 800 meter tether length that's actually being reeled in at the drum needs to be changed every week, whereas the tethers up here, from here onwards, need to be changed every 7 weeks due to just tension and UV degradation. So is it really cost efficient and sustainable to change the entire kilometers long worth of tether every week? Absolutely not. So we came up with a design to actually change only the section that's being reeled in and reeled out. And this can be seen in this image that we have here. If you see this point from here to here is approximately the 800 meter tether length. We reel it in until it's close to the secondary generator that we have on the right here. We attach a new tether onto it, reduce the tension, and thereby allowing us to replace the tether. So all in all, for any given point in time, we generate approximately 541 kilowatts of power, and we have about 19 systems. So we actually generate 240 megawatt hours of energy. The university at best only needs around 202 megawatt hours. So we have a surplus around 38 megawatt hours, or about 18%. What do we do with the surplus? Well, part of it we actually store on-site in lithium-ion batteries for about 1 day's buffer. But alternatively, the rest of it can also be sold back to the grid to generate extra profit. Now, we want to actually supply energy to the university, so it needs to be in close proximity. It has to be in the Netherlands. We also want to be avoiding heavily populated areas. So, if you can see the image, we want to choose areas that have shades of either white or light yellow. Next, one of our user requirements were to also not affect the wildlife, but especially birds. So this ruled out major bird areas in the Netherlands. Now, no-fly zones are a major no-go, and these restrictions are not going to change anytime soon. So some more restrictions are placed. And finally, we want close proximity to high voltage grid connections, as power, energy losses over transfer is actually a big problem. So the red dots are actually our high voltage grid connections. So as you may see, over here, at North Oostpolder, here is where we actually will deploy our system. Safety is a real concern for our system. And the first thing we'd like to talk about is the tether entanglement. Our system is designed to actually not have the gliders entangling their tethers, but the systems between each other could have entanglement. And although we do have an active control system for that, we do have to create an emergency system. This emergency system works in a very simple way. The gliders can actually detach from the tethers. They can fly down to the surface and just land on the grass. But the tethers itself, as you can imagine, we don't want them to just drop out of the sky. It can cause damage to the ground. So over here, we have the Y-tether connection, which actually deploys a parachute, and this allows the tether to gently fall to the ground. Now, unauthorized personnel near the site. Now, that could be a genuine problem, not just for them, but for our system as well. So we'll have CCTV cameras and active security personnel to make sure this doesn't happen. This is also like a valid solution for vandalism. And in this day and age, hacking and hostile takeovers could be possible. So in addition to having strong firewall security, the ground station should also have a manual override in case something would happen. So what does this cost for the university? It costs an initial investment of around 63 million euros. That's quite a bit, so bear with me. And a yearly payment of around 4 million euros just to keep the system up and running. But this actually, based on our calculations, found that we have a return on investment of around 10.5 years. And after this return on investment period, we actually saved the university around 6 million euros a year, which is fantastic. But how does this compare to conventional onshore wind turbine farms and solar farms? We start with the cost of production. To generate every kilowatt hour of energy, it only costs us around 5.5 euro cents. Compared to the wind and solar parks, this costs around 7 and 6 cents respectively. So this is advantageous for us. Another criteria we looked at was the energy return on energy invested. It's simply the ratio between the amount of energy our entire system will generate over its entire life can compare to the amount of energy it took to produce the system and keep it up and running. We want this number to be as large as possible. And this number for us is around 1.5 times more than wind farms, and around a bit more than double that of solar farms, which is again great for us. Now we look at the effective power density. Now this is the total power that you generate, which for us is quite a bit, over the total area that you use. This is including clearance, not just the area that is essentially required. And for us, we find that our power density is around 1/10 of what the conventional wind farms have, and around 100th of the solar farms. But as you may have seen in the image before, we have a generator for each system, a drum, but we also have a takeoff and landing strip. But for the rest of it, it's just open space, right? It's grass. We can put solar panels or cows or those kind of things. So how much of effective space do we actually use? But it turns out that we actually use 7 times less area than solar farms, equivalent solar farms, but significantly more than wind farms, simply because wind turbines have very slender towers. Now the carbon footprint was calculated using a parameter called grams of carbon dioxide equivalent per kilowatt hour. And for this value, we have found a value of 25, which is around the average value for most onshore wind turbine farms, and actually better than most solar farms. But the main thing we want to take from this is the fact that our power outputs are more consistent. How many times have we been driving down a highway and have looked at the wind turbines and said, why are they not spinning? Yeah, this has happened plenty of times. And by operating at the altitudes that we do and have the system that we have, we operate not just at high power, but also more consistently. Now let's see if we met our requirements. We designed the system to actually meet our weather requirements for rain, ice, and wind gusts. not just technically, but in terms of the operations, finance, and life cycle. Our return of investment was around 10.5 years. After negotiating that with our client, it was deemed okay, so we consider that also a criteria that we meet. It's certainly scalable to provide energy for the university and more, so that's also a requirement that we meet. In terms of the amount of area we use, we are better than conventional solar parks, but not as good as wind farms. So this was somewhat met. And finally, even though we did have a design philosophy to use renewable materials, it was found that for the performance that we wanted, this was not really possible entirely. So as of now, this requirement was not entirely met. What are the challenges our system faces for the future? Well, for one, we have a Y-tether connection over here. This system here is a conventional off-the-shelf product. And although it is very easy to buy, it is very important for us to perform analysis about friction, lubrication, and cooling. Another thing we had to consider was the legal analysis. Yeah, we considered the no-fly zones and the government regulations, but as this was considered a technical feasibility study and not a legal feasibility study, this was kept for the future. Now, another thing that you may have noticed is that this requires a lot of control. And our control system, while designed in theory, it still needs to be tested and implemented before the system actually becomes something that we can use. Now, the runways are something that not just contribute to the ground efficiency, but they also contribute significantly to our carbon footprint. So by actually finding a more efficient way to take off and land, and to reduce the number of runways that we have, it can make our system much better. And finally, we have to also be the forefront of developing sustainable materials, because in order for them to be competitive with our system, we need to be the driving factor, and which could potentially make our system more lucrative. So we'd like to thank our coach, Santiago, who's sitting over there. This is over there. Gabriel unfortunately couldn't make it, for a lot of time and more importantly patience you showed over the last 10 weeks. We'd like to thank Dr. Schmel, who's sitting in the row over here. Without his research and knowledge, we wouldn't have been able to build this system. And on the right, we have Dr. Cherubini, who actually provided the video and is also an expert in this field. And finally, our very own project management and systems engineer professor, Erin Moy, for just showing us how we can actually undertake an assignment like this properly. So, our system is cost efficient, it's cool, it operates above the clouds, and it provides power to the university. The GreenHyve is a system brainchild of mine, Mart, and my 9 other colleagues will be on the stage very soon. We're going to be soaring to the future, and we hope that you can join us. We'll now open the floor for questions. Thank you.
Okay, first question over there.
Yes, I was wondering how exactly, because the Y thing is spinning, like how do you make sure that the entire tether rotates within its own axis? Because otherwise it will spin up, right, and then entangle itself.
So your question is how we will make sure that the tether do not entangle?
Yeah, so how, yeah.
I think Caroline can give an answer to that.
Yes, thank you. In the Y connection there is actually a ball bearing that will spin around to ensure that the tethers won't entangle and spin up. And in addition to that, the whole tether is braided in such a way that it doesn't cause any twist in itself. If that makes sense. Does it answer your question?
Yeah, it does. Do you have like any, I don't know, sizing for this ball bearing? Because I can imagine it'd be very large, right? Because it has to, it's quite some force that it has to withstand.
I think Thomas can be more specific on that.
Unfortunately, I do not have the numbers here with me right now, but the model could be looked up if you're very interested. It should not be, it's not very heavy comparable to the tether itself, so it doesn't introduce any mass issues with the design. It is a little bit bigger, but that should not cause any issues anyways.
Thank you.
Question over there, gentlemen.
Yeah. Is the environmental impact of the landing strip quite material? Did you look at having, say, one landing strip and then put the whole thing on a rail, so you can launch multiple.
Yeah, so your question is whether we looked at reducing the amount of runways by, for instance, having one and then moving the generators. We did look into that. In the end, it's one of our recommendations to look further into it. We did not have the time to fully design it, as we would have to design indeed a system that transports generators or drums across the field, and it was in the time, for the time being, and enough. But definitely, that's for the future something to look at.
Second row there.
Yes, excellent presentation. Thanks for it. First question, which just to follow up on his part, was why don't you think of using a drone kind of a style which lift by itself, the space efficiency? And second, among the challenges you listed, which one you think is the most important to make this a commercial success?
Yeah, okay,
because
so
it's still not a commercial success in this field, right?
yeah, so there's two questions. The first one is why did you choose to use drones for takeoff, and the second one is what is the biggest challenge? Well, for the first question, I think Linde can answer that.
Yeah, so we couldn't really turn the rotors so they could take off like a helicopter, but we didn't opt for this because they would have the tether, and it would add a lot of weight to the system, so you would need a lot of propellant to take off.
It could drop them, the tether. Okay, anyway, we take it later. Yeah.
Okay, and for the second question, I think almost what we can answer that best. Yeah, the question one more time. What is the biggest challenge that we have in the future?
Well, currently the control systems will be is something that needs to be investigated a lot further. As the system will experience gravity on one side in its direction, and on the other side it will fight against gravity. This causes a lot of issues, additionally to having similar aerodynamic properties but not exactly the same, causing it to be to make converging of the system a very important goal for the further designed control system. So, sorry.
There was a lady over there, all the way up there.
Regarding safety, did you consider challenges like drones, whether they're legal or illegal, or birds like geese and so on?
So the question is whether we take into account, for instance, drones or birds flying around for safety. And Thomas Lokken, you again looked into that, right?
Yeah. Right. For birds, generally speaking, the birds will have a risk for their own safety, but the system will not be too influenced by bird impact. Furthermore, the drones have been looked into, but a lot further than safety with introducing a no-flight zone for drones. We could not really come, as the drone defense systems currently would induce a lot of costs on our system, and those are still very much in development, and therefore we're not considered part for our design. Does it answer your question?
Henry, you had a question.
Yeah, I'm not going to remark on the fact that you ended the Lelystad airport debate, because if you end it's clear about it. But I have some questions about the dynamics. You show a picture where in the beginning you nicely ascend vertically, and then suddenly you tilt it. But I'm really wondering, you have two motor gliders which are flying around each other, and then in a crosswind, what is going to happen? I cannot imagine that you are capable of really going up nicely horizontally. And I'm also wondering about the ultimate dynamics if you are under an angle, and you mentioned gravity, but it's not only gravity, it's also the angle of attack. So the plane moving down feels a different angle of attack than the plane moving up. And then what is going to happen? Are we going to have horrible oscillations? Do they keep turning around each other with a phase difference of 180 degrees, or is one going to catch up with the other, and then what's going to happen?
So the question is maybe about the flight dynamics and how it will behave in a flight path. I think Xander can answer that question, so if you could pass the microphone to him.
Yeah, thank you for the question. For the first part of the interactions within each other, I think it's also one of your questions. Well, at first, if you're flying crosswind, so under an angle, it actually takes about like 15 seconds for one glider to pass the point of the second glider, so it takes approximately 15 seconds. And because you're flying crosswind, in those 15 seconds, the crosswind actually blows away the wake.
I'm not afraid of the wake. That's not my question. The fact is that do you assume a constant turning speed? And I don't think that is going to be the case.
Yeah, we looked at the steady state model. So at certain points in time, we looked at the model, and at that point of time, it had similar properties. But this is actually a thing that also next to the control system, yeah, we need to make a numerical model, and once we model it, yeah, we can actually also look at all those things. We did take into account the gravity. And one more thing I want to add actually is the angle of attack you mentioned. Because you're flying crosswind, the wind speed is actually about 10 meters per second up there on average, and we're flying at a lot higher speeds, up to like 80 meters per second. So in that way, the angle of attack of the wind speed is actually, it's mainly, your apparent wind speed is mainly decided by your flight direction.
I hope that the wind speed is a bit higher. That's the reason why you went so high, right?
Yes, oh yeah.
Yeah, so we have considered gusts as part of our model and the effect of it on our system. But generally speaking, we took the average value because we did take a look at day-to-day wind activities at certain altitudes, but they were not as consistent as average values. So we designed our system for average wind speed values.
But is it stable? Are the two planes keep rotating around each other? Is one going to catch up to the other one?
So in the horizontal phase, they are stable. At the angle, when it's actually in its real out and real in phase, they are flying in circles at an angle. And this angle we have taken into account based on how we want to control our system based on the roll and the pitch of the gliders. I don't know exactly the numbers at the top of my head, but we have taken it into account. But this needs to be implemented in our control model. So we have taken it into account, but yes, it needs to be implemented properly.
Question all the way up there.
My question kind of builds on the previous question, saying takeoff. How do you assume that while the drones are on the circular runway that they stay in the middle, or because I think it'd be very difficult to implement such a way that they both have the exact same speed at the same time when they stay in the center, because they would probably deviate a little bit. So how would that impact the actual tether, and could that not introduce potential dangers that one will take off or impact?
So the question is basically about the takeoff, whether the both gliders will stay on the runway and the center of the tether will stay at its place. I think Linde has the best answer to that question.
Yeah, so the tether will be connected to the tip of the wing during the takeoff. And then the tether will be under tension, which will keep the two planes stable. And yeah, then we have to be in control to maintain the same speed.
The last two questions for the two gentlemen here. Who goes first?
Well, one of the previous questions was about birds, but one of your slides showed that the location of the system might be near to Flevoland Airport. So that very large birds are flying around there. So I didn't notice that you talked about that.
Yeah, so the question is, what about Lelystad Airport basically?
Will it be there or not?
Yeah, Caroline has taken a look into that, so she can answer that question.
Yeah, so we did look into Lelystad Airport, but the flight paths that are planned as for now seem to go exactly around our system. And in addition to that, we actually looked into some other possibilities for the system, more towards the Goeijen and also possibly closer towards Twente. There was also some grid connections there and some, well, fewer people living there, let's put it that way. So we have looked into that for sure, but considering the development time of our system, by then we will probably know what Lelystad Airport will do.
Okay, so you care about the people and the birds.
And the big birds too.
Well, my last question then.
Okay, connected to the question of Henry. You emphasized in the beginning that you are flying crosswind. When you have a rotating system, the wind will come from one side, and you will have tailwind during a quarter of the rotation and headwind during the
So the question is about the flight path, whether if you're flying crosswind, they would have tailwind and headwind in parts of the circle. And basically, we can show it a bit with the model. So it will be flying at an angle, and the wind will be coming from the direction of my head, possibly. And if they start turning around, you can see that the wind will always be in the same orientation towards the glider as in other parts of the circle. So the thing about crosswind flying is that they never experience headwind or tailwind, but they will always stay in the crosswind, so the circular path will be in this plane somewhere. Does that answer your question?
I would like to see a simulation of that.
Okay.
Okay, thank you very much.